Okay, well, welcome everyone. I'm going to get started. So first, thank you so much for taking some time to attend this webinar on OptiStruct optimization. As we kind of get rolling here, I'm going to kind of kick off a couple polls just as I kind of go through some introductions. So feel free to kind of go through some of these questions while I kind of go through some introductions. So first, my name is Drew Buchanan. I am the engineering manager here at True Insight. If you're unfamiliar with who True Insight is, we are the channel partner for here in the US. Happy to be here and talking my own background. I spent about a decade in industry and both primarily in energy, but a little bit in biomedical. So I've used optimization for a lot of different applications. And the previous decade I spent in the reseller space. So excited to be here. So if you're unfamiliar with who Altair is, they're a high-end CAE company. And really, they allow engineers and designers to leverage making engineering design decisions all you guys are making through the use of simulation, HPC, and AI. We're talking solely focusing in on one tool today, which is OptiStruct optimization. Altair has a very large suite of tools. If you have questions, we don't just deal in physics-based simulations like CFD or FEM. We're in analytics and IoT, as well as design modeling visualization. So if there's something you're encountering, just let us know. Shoot a message in the chat. My colleague is monitoring the chat. Also happy to chat after this call as well. More often than not, in the Altair suite, we probably have a solution that can help you out. So the agenda for today, we're going to focus in on OptiStruct optimization. Kind of talking about the different types within the suite, then looking at some best practices and questions. Obviously, it's a 45-minute webinar, so I'm not going to be able to cover every single thing, but I wanted to kind of run through a couple different examples and some of my own best practices. The other thing to keep in mind, I'll save some time at the end for some questions. But if you have questions as I'm going through the presentation, my colleague, like I said, is in the chat, so he's able to answer any questions, and then we can save some time at the end. Great. All right. So let me jump into what exactly is OptiStruct. Looking at the poll, there's some of you who are using Altair, and then some of you who aren't. And OptiStruct is one of Altair's legacy solvers. Primarily, OptiStruct is an implicit-based solver. We also have an explicit-based solver, which is Radios. But OptiStruct solves a variety of problems, specifically within the FEM space, so structural, like linear and nonlinear and multiphysics, et cetera. But one of the things that's really unique about OptiStruct, and obviously why you guys are attending, is optimization has become so prevalent in the past few years because of additive manufacturing. OptiStruct has actually been kind of the industry leader. The first, it came out in the early 90s. Was one of the first optimization tools out there. And as a result, we've had a lot of time to kind of develop the tool and utilize the tool in a lot of different ways. So like I said, looking at optimization first in fail-safe topology, multi-material topology, and multi-model optimization versus some of the other tools out there. They came after OptiStruct and they don't necessarily have as much feature and functionality. Lastly, OptiStruct Solver is actually utilized across a number of our multi-physics tools. So Altair Inspire, which is our designer-based tool, SimLab, which is kind of a little bit higher end tool, and then HyperWorks HyperMesh is our kind of analyst-based tool. So the ability to actually solve optimization can be solved in all of these three programs. All right, so let's jump into what actually, some of the types of optimization within OptiStruct. So I'm guessing most of you who've heard of optimization probably are familiar with topology. Topology tends to be the most prevalent across, a variety of tools. Topology being, you have in this picture, you see you have a couple of constraints. You're going about, let's just say we're setting up a basic linear static study, and the linear static study has some restraints and material properties. And you see everything in that kind of red magenta is where you're removing mass. And then everything that's silver, that's known as a non-design space, whereas red is design space. The silver does not have any mass removed. The advantage of this is you can kind of maintain your structural requirements while reducing a lot of mass, which can be very advantageous for a variety of things, but primarily cost per year. If you're manufacturing, like in this case, this bracket arm, saving mass is going to save you a lot of money and time. The topology optimization can be utilized in Altair Inspire, Altair SimLab, and HyperWorks. So a key thing to recognize, OptiStruct is the solver. It's the engine that's solving all these optimizations. When you sort of see me going through Inspire, SimLab, and HyperWorks, those are the programs that you're running the OptiStruct solver in. Topography was generally used for sheet metal. You kind of see this oil pan example where you can optimize beads, can be very advantageous for sheet metal applications. And then the other really prevalent example I run into and I work with a lot of customers on is free size optimization. If you're working in the composite space, this is a super advantageous tool because it allows you to adjust the optimization based on a element by element basis. I will talk about this a little bit further in this webinar, but when you look at topology, the density is fixed, so you have kind of a uniform thickness in terms of how you're removing. Whereas with free size, you can actually adjust on an element by element basis, which means you have variable thickness. So if you're laying up plies, you can actually specify the different ply thicknesses, which can be very advantageous in composite design. And this, as a result of composites, you're going to be working in HyperWorks HyperMesh. Some of the other optimization types, shape optimization. This is also a very useful optimization. I'm going to run through an example on that. Shape optimization works off you provide a number of set shapes, and then you kind of utilize the optimization to kind of come up with an optimum shape, as a summation of those shapes. A great example would be like a beam with a various different kind of types of shapes, or maybe like a heat sink fin where you kind of extend the fins. That would be an example. And again, it can be optimized for stress and displacement or temperature. Gauge optimization, you kind of see in the yellow right here, that's looking at a sheet metal thickness, and blue, varying thicknesses. You're optimizing that gauge thickness within sheet metal. Free shape is kind of a combination of free size and shape optimization. You kind of see this picture right here where you actually have a high stress concentration localized around that fillet. And by just changing a couple nodal locations, you can actually sort of kind of reduce that high stress concentration on, one around that fillet, but also on the bottom surface. You notice the stress is reduced. So it's a way of just manipulating and moving nodes around to kind of meet your constraint and objectives. Okay, so let's jump into a demonstration. I know I'm looking at the poll right now. Some of you've never used optimization, some of you have. So let's just kind of get our feet wet with the tool and kind of go from there. Great. So the first tool I'm going to show you is just a pretty basic tool. So it's known as Altair Inspire, but it's very powerful in its capabilities. So it's this tool, the intention is for a designer based. Maybe you're not doing FEM every single day, but it has that capability to run optimization. One of the things that's really nice about our tools is that we're CAD and solver agnostic. If I wanted to import from my CAD, I can. The other cool thing about this tool is we can actually kind of create some geometry. So I'm just going to create some geometry real quick, just to kind of give you a feel for the setup, if you've never run optimization before. And we will build on this. We'll look at some more advanced examples, but I just want to kind of get our feet wet first. So first thing, if you've never used this tool, you can kind of dimension and set things up however you see fit. If I want to go, by a dimension here. And again, for the most part, most of your use cases in this, I see customers actually importing into this tool, but I just wanted to kind of show an example of actually creating a geometry. Okay, so let's specify a geometry here. So now we have our geometry set up. We can go through the actual process. The great thing about having a optimization tool at the designer level, there's actually some pretty cool things you can do, focusing on polynerbs, which is actually kind of adjusting the surface after you run an analysis, as well as being able to kind of tweak extrusion, et cetera. But let's kind of go through the process of setting up the model. We'll keep it pretty simple to start with. I'm going to specify a constraint on the end right here. So this is what I'm applying is I'm fixing this space right here translationally. I'm completely fixed, and then I'll apply a load in tension. So great, we've applied the load and tension. We kind of work our way from left to right in this tool. In Inspire, we can specify our materials, and then we can actually specify, some of the kind of cool manufacturing controls when you run optimization. So, one of the things that we do a lot is we work with a lot of DFAM, but also subtractive manufacturing. So, if you need to actually kind of maintain a constant extrusion, we can specify that when it actually removes mass from the system, because what topology optimization is doing is removing mass, we actually have an extrusion-based command. Some of these other commands like draws and split draws and overhang, they pertain to additive manufacturing requirements. So the cool thing about it is we actually have those manufacturing controls built where that will actually also allow you to remove mass in a way that is conducive to your own manufacture. We can also kind of utilize symmetry if we want. Symmetry would mean that if I'm removing mass in the system, I click on the design space here, and I can specify, I want to remove mass to be symmetric across these planes. I'm not going to apply symmetry just for the sake of time. And then the other thing you need to do is you just need to specify the design space. You'll see as I kind of step through this, I'm actually going to show an assembly because you can use assemblies within this tool. But we have this set up at the part level. When I look at when I click the hit optimize here, the cool thing about this from a designer-based optimization tool, you still have a lot of flexibility in the types of studies. A lot of designer-based optimization tools are only looking at topology. Because OptiStruct, we've had this tool for a long time, been able to develop it. We've actually integrated some of the advanced optimizations within this tool, like topography, gauge, and then even basic shape optimization. And generally, when I'm jumping into shape optimization, I'm jumping into HyperWorks, and that's going to be the example we look at later. But you can do some shape optimization. Another kind of common application I see with a lot of customers is lattice optimization, which you can do within this tool. So we can specify our objective is to maximize stiffness. We can also say to minimize mass. In this case, I'm going to maximize stiffness or compliance, and specify how much mass I want to reduce. At that point, I can run it. I already have a case here, which I can just show you real quick. And this is kind of your typical output when you're looking at results. The nice thing about this is we can actually, fit a polynerbs to this. So those of you who are actually sending this to your 3D printers, we can actually, create a parasolid shape that you can sort of send to your printer. So it's kind of a full kind of analysis tool. So what the shape is showing you is based on the load I've applied. I don't necessarily need to have a full surface on this end right here. Everything that's magenta is still there, and everything where it's kind of translucent, that's okay to remove mass from. All right. So that's kind of a basic example. We'll kind of jump into some more advanced examples in a moment. But you kind of see as I step through that optimization process, the main thing you'll see is there's an acronym I use called DRCO. You'll see it in a lot of Altair forums. But even if you're, this term's commonly found in other CAE tools. So the first thing is the design variables, what you have control over. So in topology optimization, you're specifying a design space. That's your design variable. So you're saying I can remove mass from that entire design space. With some of the other optimizations like free size optimization and shape optimization, which I'll show, you're actually specifying the design variable as maybe the thickness, or maybe you're doing composite optimization and controlling your ply drops, things of, kind of design variables or parameters. Responses would be what you're measuring. So most cases, people are running optimization for some type of structural analysis. Maybe it's a thermal analysis, but let's just say you're running a structural analysis. You might be monitoring your critical stress. So you might not want to be going above your yield strength because you don't want to have a permanent deformation. So that's typically a classical response you might have, or maybe a key displacement. The constraint is when you kind of, how the software actually removes mass from the system. So say your stress value is you want to be 1/2 of yield. Your response would be, I want to be less than 1/2 of yield, or, making sure that I'm not having, when I'm removing mass, exceeding that criteria for my constraints. And typically our objective, as you kind of saw, you're kind of minimizing or maximizing systems, whether it be stiffness, which is compliance, or actually minimizing mass. So I have a couple tips. I want to kind of focus in on topology because it tends to be the most prevalent before I jump into some more advanced applications. The first thing is mesh size. This is across the board in any topology optimization. You need to have a good kind of mesh quality. At bare minimum, when I say minimum member size, that's referring to the minimum thickness that you're going to specify in topology of your walls. It should be at least 3 times greater than the mesh size. So if you have a really coarse mesh size and this isn't working, that's a kind of an indicator to you that you need to make your mesh density a lot finer. Same thing with maximum member size. It's about 6 times. And these are just general rules of thumb. I'm not saying you need to be at, this is what you should always use, but this is kind of where you should start. So again, 6 times the mesh size. A key thing I see in a lot of support tickets, or when I've kind of been training customers, is their mesh density is not great. It's very important to have a good mesh density when you're running topology optimization. The next thing that I kind of run into a lot is, especially, most of the time, optimization is done from an assembly-based level. And when you're dealing with assemblies, you obviously have contacts within OptiStruct. So like your tie contacts, how parts are connected to one another, how they interact. A lot of times you may neglect your contacts. One of the things I'm going to show you a tip is a way of checking if your system is properly constrained. So making sure your systems are properly constrained is going to help you avoid inaccurate optimization. I'm going to show a tip, something I recommend and something I do before every optimization, but actually in a lot of cases before I do any type of structural analysis for assembly, I'll kind of show you a tip to how you can check your constraints in a system. Lastly is improper constraint options. Like for instance, like you have a constraint where your stress, a value that you're measuring is like, you don't want to go above a critical stress value, but that stress value is so minimal, you're always going to be kind of exceeding that criteria, and you may always get a topology optimization fail. So that's something else when you check your logs in OptiStruct is check your constraints. It's generally a good rule of thumb to run a linear static or not whatever type of an optimization you're running, an actual structural study first, so you understand that your stress and displacement constraints you're applying make sense. All right, so let's jump into a demonstration. I'm going to show you a tip for checking your constraints, specifically if your system is constrained or not properly. So I'm going to close this file, open this. So I'm going to open up an assembly model here. So I wanted to at least show you and inspire you can take advantage of assemblies, especially with optimization. So again, it's still a pretty powerful tool, even though the GUI is very easy to utilize. So you see everything that this block in red is where the actual design space is. So that's where you're going to remove mass. One of the things that you need to check is you need to check your contacts. So in this case, what I've actually done is I've actually, every kind of connection or contact I have with these different parts, I've actually specified no contact. The reason being is if you think about FEM, every one of these tools we're using, whether it's Altair or one of the other tools, it's a numerical method. So there's theory behind everything we're doing. One of the things that I was taught early on in my career was when you start dealing with assemblies, it's kind of hard to probe your connections, every single one. Obviously, this one's kind of simple, but with a larger system, one of the things we know from theory is the idea of rigid body modes. So with natural frequency, you can actually determine if your system is constrained properly by rigid body mode theory. Meaning, if you run a natural frequency case within those first 6 modes, you have a resonant frequency is not a zero-based value. So I'll show this to you. If you've never run resonant frequency, this might be kind of a game changer. I know when I was first learning this and my mentor showed it to me, it definitely helped setting up my FEM cases a lot easier for assemblies. So like you kind of see in this model, I have some loads and supports. You kind of see them, and I just kind of showed you that there's no actual contact, so technically these things can move through one another. One of the cool things you can actually do in Inspire is you can actually run a normal mode study. So this would be a natural frequency study. I can specify the number of modes. You need to run at least the first 6, which are the rigid body modes, which pertain to the translational and rotational restraints in your system. So make sure you reference the load case when you're setting this up. So when I actually look at this case now, and I change this to normal modes, if I look at my first mode, see how it's just the parts are flying away from one another? You can tell quickly that they're not connected to one another. The other kind of key indicator you can look at is that the value is between 0 and 1. It's a zero-based value. So this is something I do all the time in setting up structural studies for assemblies. You don't even have to be running optimization. Run a natural frequency study first, a modal analysis, and check your first 6 modes. If you have a value that's 0, and if I hit animate, you can kind of see where the connection there is not good. So this is a great tip in CAE to utilize, and something you should probably always be doing in optimization to make sure your connections are set up. So let me kind of open up the case that's constrained, and you'll actually see that these values are going to change from 0 to actually being a non-zero value, which telling me that the system is constrained. All right, so I'll go to constrained right here. I'll go to the same exact analysis, and now you see when I go to normal modes, that the first 6 are now not, they're greater than 0. I can also, if I animate this, you'll see that it's moving together as 1. So definitely, if you're not using this, it's something I recommend doing, not even an optimization, just for structural analysis. It's usually the first analysis I always run in CAE. Another kind of cool tip before I transition to jumping into HyperWorks is there's a nice, pretty cool compare tool. I'm looking at the poll. Some of you are actually in HyperWorks, so you're probably using HyperView, which will show later. But maybe some of you who are not within our tools, there's actually a pretty cool compare tool within Inspire for optimization. So when you run these optimization studies, I can actually run different configurations. And you kind of see right here, here's my first configuration where I ran optimization on a case with proper contacts. If I click on it, you'll see the other contact, and you kind of see the thicknesses start to change a little bit. But there's also a pretty cool feature where if I click on it within the actual kind of results view and hit compare results, it'll actually show me my compliance for these different cases. The first case is reducing 30% mass. The second case is reducing 25% mass, which makes sense in terms of our stress compliance. You have more mass left in the system. It's the stiffness is a little bit better. But we can also look at actual individual results here. So if I want to go to comparing my structural results, you kind of see between that 25 and 30% case, I can look at von Mises stress and factor of safety. I can look at these values very quickly, and I can have a lot of different studies. So you can kind of even see above some of my kind of precursor studies before running optimization. They're here as well. So that's another kind of cool tip within the Inspire space. I just wanted to show real quick. All right. So let's kind of jump into some more advanced examples here, and talk about moving away from topology optimization versus free size optimization. So you kind of saw in those examples when it was removing mass, it was doing it to the entire design space. That's how it was removing mass, but it wasn't doing it at like an element-based level. Free size optimization can be very valuable because it allows you to kind of specify the thickness of each element, and it can be variable thickness across the system. Why has this become very useful? If you're someone who's designing within composites, it's really important to have a good bending representation. Otherwise you're not going to get very valid results. And so you kind of see both of these examples here, taken just straight from the OptiStruct user manual, run the exact same case, free size, and then topology. You kind of look at the topology example, and the models on the right of these, which are kind of like the green colors. On the topology example, you kind of see everything's kind of a uniform thickness, because the design space, the design variable is your density. In this case, the actual thickness is varying because you're varying the thickness across each individual element within free size. Free size, like I said, it becomes very useful in composites. For the most part, these are the two most common optimizations I see customers do. I'm going to show another one, which is shape optimization, which also I'd say is pretty common, but these tend to be the most common. And free size tends to be advantageous for composites. So let's jump into an example, and we can actually see this within the HyperWorks context. Right. So again, I know some of you are using HyperWorks, and I think there's a lot of you that are using HyperWorks, so you're probably familiar with this, but just to reiterate, kind of the cool thing, HyperWorks is the new interface. Some of you guys may be using the legacy HyperMesh interface. I ran a webinar actually last month. If you haven't seen it, I actually ran through some HyperMesh tips and tricks, and kind of talked about running it within the new interface. I'm still using HyperMesh here. I'm using it within the new interface. So the first thing to kind of point out is we have those capabilities to actually import different solver decks. When dealing with composites, this is something I do a lot with customers that are coming from, maybe coming from CATIA, maybe you're coming from Abacus or ANSYS, or maybe you're using our tools as a pre-processor and then exporting out. We have those capabilities, but obviously in this case, we're actually using our advanced optimization algorithms to run this. So there's a lot of power within our algorithms in terms of running. So we're actually going to run this case, but I wanted to bring up that we are solver agnostic. All right, so what exactly do we have showing on this model? What we have is we actually have our actual composite, and this is going to be an example of free size optimization. So in composites, one of the things that you're typically worried about is we're worried about our overall ply thicknesses. So in this case, we don't necessarily know what's an optimum ply thickness. I'm just starting off with a relatively thick ply, and then I actually want to run a composite optimization, so a free size optimization, to determine to me what that ply thickness is going to be. So we can actually do that. We can run a stress-based test, and you kind of see the actual loads right here. These edges are being restrained. That's the actual constraint. And if I go to my model browser right here and go to my loads, which I open up my loads right here, you kind of see just a point load on the end that I'm applying. And you kind of see that magnitude that's being applied at that specific location. So within the actual HyperWorks case, one of the things that's pretty cool, even though it's a really sophisticated tool, the user interface is still pretty easy to utilize. With the newer interface. In the old interface, how you'd find everything would be based around the panels perspective, which some of you guys may be familiar with. So if I click on free size optimization, the first thing it's going to ask me for is my actual design variable. So my design variable, if I click on it, this is really what you're kind of controlling here. Like I mentioned in my earlier slide, what you have control over. In this case, I'm specifying it's a free size optimization, and I'm looking at if I wanted to actually control my ply thickness, what my max ply thickness could be, I could do that. In this case, what I wanted to drive the system because it's just a temperature value, is just my ply drop. You kind of see what my ply drop max can be. And then also, what my ply percentage could be. So it gives you kind of the option that where you can see, we can start to kind of customize and utilize these values a good bit. So that's our first value. That's our design variable that we're setting in the system. Again, a couple rules of thumb when doing this. Good mesh density, kind of that mesh size accordingly, something to kind of be aware of when you're setting things up. If I go to my optimization response right here, key thing is compliance. I think I actually have up here, this is the compliance equation. So if you're unfamiliar with that term, that's just a way of kind of maximizing your stiffness, your K stiffness value, your F force value. That's a way of kind of maximizing your stiffness. So that's why you'll see in OptiStruct, that's what compliance represents. And then our optimization constraint here, this is just our volume fraction in terms of what our limits can be, in terms of what our volume is going to be. And then our final objective here, if I click on this, you'll see that it references the response. So this is, I want to maximize my stiffness. And then it also references the load step case. So in this case, I kind of showed you the constraints, and there's also kind of a point load on the end. So when I actually, run this case, I can actually look at the results. One of the nice things at the new interface, there's actually a built-in result view without having to change to hyperview. I will show an example of shape optimization jumping into hyperview. So those of you who've used hyperview, that's fine. You still have access within the new suite, but I just want to show, something quick in terms of the results here. So I click on my results. This references the H3D files, which are the hyperview files. And then we can actually take a look at the individual contours here. So what I'm actually showing here is the individual element thicknesses. And you can kind of understand this was totally optimized to actually represent the different thicknesses for each individual element. I can also, if I wanted to, if I go to this plot right here, I can go to ply thicknesses, and then I can actually look at my ply thicknesses. So this again gives you the option of actually being able to optimize and set up your systems, and you can also export this back out and import it back in, when you're actually building your plies in the composite modeler. So really the usefulness is of being able to actually get an accurate ply sizing and ply thickness within free size optimization. Great. Let me jump back in. So let's jump into shape optimization. So again, a couple of best practices and best tips. So the way shape optimization works is that you kind of have your initial design, as you kind of see on here on the left, and then you have certain shapes you can manipulate it to, and then the optimization algorithm will actually utilize those different shapes and kind of give you an optimum shape. So you kind of see the final design doesn't represent any of the shapes I specified. It's kind of summing those shapes together to give the optimum design. And the requirements would be very similar to what we've seen so far, like whether it's a stress value, a displacement value. I'm going to show you an example where I'm optimizing around temperature, but this is kind of a pretty cool tool in the fact that it can kind of give you that final shape of kind of the summation of the shapes you have. One of the key requirements for this, as you kind of see, is you have to have something that can be continuously differentiable. In kind of layman's terms, it's something that can be easily morphed. You can kind of move that mesh and morph it. Where shape optimization tends to be most useful is if you have kind of like continuous shapes like fins or brackets, linkages, beams. I see a lot of people optimizing their specific beams within shape optimization, or like basic heat sinks or things like that with very kind of continuous extrusion based shapes. When you start dealing with like organic shapes and more complex shapes, you're going to be better off with topology optimization. Last thing is when you kind of set up your shapes, you just want to make sure your shape variables overlap, and we'll step through that as we kind of step through an example. All right, so let me jump to another example here for shape optimization. I'm going to close this model down. I know I'm covering a lot. One of the things that it is a good tip here, I'll show it real quick, is when you're going through a new interface HyperWorks, I recommend you click on Help instead of Tutorials, because Tutorials, it'll just show you the HyperMesh tutorials, but what you can actually do with the Help active is scroll to the bottom here and then click on View All Simulation Help, and then click on OptiStruct, and then click on Tutorials. You'll get the OptiStruct specific tutorials. In this case, we're dealing with HyperMesh, which is the HyperWorks interface I'm working in, and you can kind of see some of the different optimization tutorials you have at your disposal. There's a good bit. There's so many of these tutorials that, when you actually, go to work through them, you're gonna have to download a tutorial model, but that's right on the Altair portal if you need it. All right, so let's take a look at this example. So this is an example kind of very, perfect for shape optimization. So this is just a heat sink, and there's some fins right here. And we have the ability, these fins are just, machined out. So we have kind of requirements where we can kind of adjust the overall size just via basic tolerances. We can kind of know where we can go in the upper and lower bounds. As far as what the actual system is, it's already meshed. The actual load we're running is just a basic temperature value. If I show the temperature value just being applied at 283 degrees, 283 degrees is what we're applying. So one of the things we want to optimize in the system is we want to specify, we want to optimize so the actual, so if I show the actual response here, measuring temperature at this center node right here. And what we're actually optimizing, if I go to the overall objective here, is I want to minimize this temperature. So I want to actually reduce this temperature value. And the things that I'm going to kind of adjust that, as we know from thermal analysis, is if you change your fins, that will ultimately affect the temperature distribution. So the actual variables that I'm setting up, I come back to my model browser here, and I go to my design variables. Note, when I actually created this model, again, I just specified shape. This would be our first step, is creating our shape variables. And if I go to my design variables here, you'll see my first shape, if I show it, is right here. So this is the actual tolerance here of where I can move it in and out. And one of the things you specifically do when you create these shapes is you kind of morph the element set right here. So that's why you kind of see this representation here. And this shows you the lower and the upper bound. Our second shape right here, this is our morphing that I set up in the system, our lower and upper bound right here. And then we also have our final shape right here, our lower and upper bound. So the cool thing about this is you're kind of you're giving the OptiStruct a number of shapes, and we want you to actually solve for the best shape between these three fins we've set up. So what we can actually then do is I solve the problem, and we'll take a look at the actual results within Hyperview. So if you're unfamiliar with Hyperview, it's our post-processing tool, very powerful, allows you to kind of view lots of results at once. You kind of see on the left right here, I'm actually looking at the actual iterations of the shape change. So you can kind of see iteration 0, that's the initial shape, iteration 1, iteration 2, to our final converged iteration, which is iteration 4. All right. All right, so great. That's our final shape, but did it actually kind of reduce that temperature, which is what I wanted to do? So if I go to my second plot right here, this actually has our temperature results showing. Kind of see our grid temperature. And so let me go to the first iteration here, and you see the original shape. And if I zoom in here, see the maximum temperature is at 298. We also note it's not as kind of uniform in terms of the temperature gradient. It's kind of not as uniform in the system. If I run a shape optimization, which I did, if I go to iteration 4, you'll see that, hey, the max temperature dropped to 288. The other thing that's kind of cool about it is you kind of see a much more uniform temperature distribution. The shapes are still within those bounds that I specified, but it's a lot larger. And that makes sense because there's more surface area for those fins to kind of transmit that heat. So it's not maximizing around that node. So this is just another example. Bear in mind, I just wanted to show temperature. You can use shape optimization for, temperature value, stress values, displacement values, even something I talked about earlier, which is natural frequency values. So just keep that in mind. That's another good tip. And you'll note one of the other kind of best practices when you start dealing with shape optimization, you'll note a lot of these elements are actual brick or hex elements. The reason being is because you have to morph them. It becomes more advantageous when you start doing morphing to use brick elements. It's just a lot easier to do morphing. So if you're going to do shape optimization, another kind of tip I recommend is to try and mesh your system with hex or brick elements, which you can do within HyperMesh. Okay, great. So the one final thing I wanted to talk about, obviously I didn't get, it's hard to cover every single feature with an optimization, with an OptiStruct. There's also tons of different, I won't say an infinite number of ways, but there's different pattern features, different control features. I want to make sure I maintain symmetry. I couldn't run through all those features, but kind of gives you an overview of the types of optimization with OptiStruct. But one of the other cool things within the actual Altair suite is another type of optimization. It's more based around kind of a design exploration based approach, meaning that I set up in one FEM study, in this case, say I set up an OptiStruct static study, and then I can export those results, export that FEM study to HyperStudy. And HyperStudy, what it will do is actually run all the cases for you. But the thing that's useful about it is it has some like advanced data mining where you can actually kind of track some plots and correlation matrices. So to keep that in mind, the other thing that's cool about this tool is there's integration across the entire HyperWorks suite. So maybe you're not even running OptiStruct, you could be running Motion View, or you kind of see Flux, or even some third-party softwares like ANSYS and Excel. We can also run those in HyperStudy. I just wanted to bring that up real quick. I know our focus was on OptiStruct. And kind of the last thing I will say before I turn it over to questions, everything I talked about is going to be up on our YouTube page. We post a lot of things on our YouTube page. Last month's HyperMesh webinar I ran is up there. You also noticed in this webinar, you can run optimization within SimLab. I talked about some of those optimization features in the SimLab webinar I ran previously. So definitely check out our YouTube as well as our blog, and keep an eye out on LinkedIn and Twitter for future events. I know we're running an event on power simulation, PSIM, in the next few weeks. So if you're doing any type of electronic design, check that out. But with that said, I am going to turn it over to questions. Thank you all for attending, and I will stick around in the chat with any questions you guys may have. So Jorge, yeah, I think as far as like airplane fuselage frame, like IC beam cross sections, hopefully that shape optimization kind of gave you a feel for that in terms of your beam cross sections. What you'd do is you'd have a couple different variable heights within those design shapes, and then from that perspective, you'd have those would be all of your. So if I come back to HyperWorks here, you'd have a bunch of different shapes of those variable heights. So if I click on each of these, you'd see in your case, in your beam for the fuselage, you'd have a couple different beams applications of going through this. I think does that answer your question in terms of how you'd want to approach that? Okay, great. Good question. Thank you. Typically, with shape optimization, you're using solid elements. I believe you have to use 3D elements. I'd have to check on that. But I think it's limited to 3D elements for shape optimization. With free size, like you saw, I was using shell. Topology, you can use shell, but I think with free shape, you have to do that. Let me just do a quick check. I'm going to stop sharing. I can just confirm that for you. And while I do that, for those of you, if you have any further questions, just feel free to put them into the chat. So you can use shell. Yeah, there are capabilities for using shell. So good question. I know when I tend to use it, it's generally with 3D, but you can use shell capabilities. Good question. Great. I will stick around the chat. I know we're at the end here. So for those of you who attended, thank you so much for attending. I will stick around again if anybody has any final questions, but if you don't have any more questions, I hope you all have a good Friday. And definitely, if you ever have any questions about anything, just let us know and feel free to kind of reach out to us in the next webinar. But like I said, I'll stick around for maybe 5 more minutes if anyone has any final questions.